How's it going, everybody? In this video we will begin our Eigrp overview and breaking down just a high-level overview of the different pieces and parts to Eigrp, the things that we're going to cover in Eigrp, and then the details and stuff like that go into a lot of the concepts that we're going to be talking about as we go along. And this is more of a setup video to let you know what we're going to be covering, how we're going to, what we're going to be looking at, and what you can look forward to throughout the rest of the session. And it's Eigrp isn't a very complicated protocol to work with. As a matter of fact, the majority of customers and clients that I've worked with that run an all Cisco shop typically run Eigrp, and it's ironically enough, it's most of the time if they're going to run one particular address space, like the 10 network, they just type in the network 10 all, and then they're done. They don't really rely on anything else to work. So I'm more of an OSPF guy myself, but we'll talk about that more in detail when we get to OSPF. But Eigrp from the high-level overview is actually really easy to protocol to work with, and if you know it to any extent, any decent level, it's actually really simple to work with. So the idea behind Eigrp is, and I have to be careful where I tread here because I don't know if the exam is going to ask you if it is if Eigrp has been released to standardization. Now, Eigrp technically still is a Cisco proprietary routing protocol. Now, with that being said, there is a draft revision out on the IETF or IEEE, one of the two. I think it's the IETF or an RFC. And what they've done is they've actually released Eigrp to be used by other vendors other than Cisco. And now, like I said, I don't know if they're going to cover that, but if they do, Eigrp is still a Cisco proprietary protocol, unless it specifically states anything about it being released, or if it says is Eigrp still a Cisco proprietary protocol, or I haven't taken the new updated exam. I took the old 642.902 route exam, and they did not ask that question. But then again, back then it wasn't released yet. So, but that's a general idea for it. Now, Eigrp is both a distance vector and a link. Actually, I should say, has both distance vector and link state behaviors. It's an advanced distance vector routing protocol. And the idea behind it, all the features that we're going to talk about coming up here are going to explain why it's an advanced distance vector protocol and why it's got both attributes. So, the first feature we're going to talk about is being classless. So it supports variably length subnet mask and summarization. You can do manual summarization and automatic summarization. In 15.x, or so 15.0 code and later, so 15.1, 15.2, so on and so forth, automatic summarization is disabled by default. So no auto summary is already enabled. So you don't have to type in no auto like you do in RIP. You just have to type in router, Eigrp, whatever, the network command, and away you go. It does support variably length subnet mask, so you can break down your networks into you can very easily scale them. And we'll talk more about manual summarization later on, and how that is probably the one that is probably the most widely used scaling tool for Eigrp that there is, because a lot of networks you might run Eigrp in your entire environment, and if you have a very large, say, retail environment where you have, we'll have company like this is just a generic, no company in general. We'll have like company has a few headquarter sites. It's got a couple of DR sites for replication for critical systems and stuff like that. Then we have a bunch of regional sites that it's going to use for day-to-day operations. And let's say for instance you have a major city like Chicago or Milwaukee, are the two closest cities that I live to, and you have these cities. And let's say you've got several. Let's say your headquarters are in New York, so you would have a connection from the New York site to the Milwaukee site. And let's say inside the Milwaukee site you've got, in the Milwaukee area, the greater Milwaukee area, you have 50 stores spread throughout the Milwaukee area. So all these sites would peer to the regional site of Milwaukee, and so a city near where I live is Racine. It's not a well-known city, but it's still a city near Milwaukee. So let's say there's a store in Racine. Racine would peer with Milwaukee, and then Milwaukee would peer with New York. New York being the core site, and then so Racine would send all of its routes in a summary to Milwaukee. Milwaukee would send all of its summary routes, so all the routes that it has from all of its stores, it would summarize it to a single route, and then it would advertise that up to the New York site. So it'd be a single update. And that's how you can scale thousands of routes into a couple of routes. So I'll talk more about that in detail later, but just to give you a high-level overview. It uses its own transport protocol, IP protocol 88. It uses the RTP, or Reliable Transport Protocol, not to be mistaken with the Real-Time Transport Protocol, or the protocol that is used for active live streaming voice. So when the words that are coming out of my mouth right now and they're streaming to your computer, if this was EIGRP, if this was, if you were to break it down, you might see RTP in the stream because of the fact that you hear voice. Not exactly sure if that's the case, but you know, that's just to give you an idea of just not to confuse you with a terminology mismatch. So EIGRP uses multicast to 224.0.0.10, and it also uses unicast. It uses multicast to discover neighbors and form adjacencies, and then it uses reliable multicast with sequence numbers and acknowledgments to make sure that everything stays up to date, and it uses unicast to synchronize unicast routing topology. So pretty straightforward for the most part, but it's important to understand the details to that. And we'll get into all of that coming up. So like everything I'm covering right now and to the end of this video, we'll go into the details of how each one works. It forms active neighbor adjacencies, so it guarantees packet delivery and supports partial updates. What that basically means is if you send an update out, you're going to receive an acknowledgement in return. And it does support partial updates, so you can send an update. So for instance, you spin up a new subnet on a particular router. You add that interface or whatever to, or that VLAN interface or the SBI to a switch or a new sub-interface on a router, and then you forward that up, and then that becomes a new route in EIGRP, and then that information is flooded as far as the query domain goes. The query domain will not go any farther than what you scope it to, and we'll talk about that coming up as well. So the update will only go as far as the autonomous system stretches, or as far as the query scoping limit has been set to, whether you've set up stub routers on EIGRP spoke sites or you have summarization enabled. It guarantees a loop-free topology. So basically the idea behind here is since we don't have a full copy of the database of the network, dual diffusing update algorithm is performed to determine best routes. Sorry about that. So basically the idea is this. You have three different tables inside of EIGRP. You have the neighbor table, which is who you're directly connected to, okay, and on what interfaces you've learned them on. So if you do a show IP EIGRP neighbors, that's where that information is going to be seen from. Now you take that information right there, and you're going to learn all these routes in. Now EIGRP has another table called the Topology Table. So show IP EIGRP topology. You take all of the routes that you've learned from all of your neighbors, and let's assume that all of your neighbors have neighbors attached to them that you learned that you're learning updates from as well. So the neighbors of your neighbors send your neighbors routes, and then all of those routes that your neighbors learned from their neighbors are advertised to you from your directly connected neighbors. So those routes all come in, and all those routes go into what they call the topology table. So the topology table is going to house every route that you've learned. Now EIGRP is a distance vector protocol. It only knows what the directly connected neighbor told it. So it looks at it and it says, okay, I'm going to take all these routes, and then dual is ran on every one of them. Dual is ran, and we'll talk about the metric and coming up here in a minute, but the idea behind it is it's going to take a look at the metric and where it was learned from and all the other variables, and then based on all those individual details, a computation is ran on those details, and then whatever ones come out with the best overall reachability details, those details or those routes are installed in the routing table. And that's a general idea of how EIGRP works. The same similar concept and processes work with OSPF. We'll talk about those more in detail when we get to OSPF. Fast convergence, and no, I'm not talking about EIGRP fast reroute. I'm talking about EIGRP and feasible successors. You have a successor and you have a feasible successor. Because EIGRP will have what they call as a backup route already pre-calculated, what ends up happening is if only a successor exists to reach a destination and you don't have a feasible successor, what's going to end up happening here is you're going to have routes that will have just a single path to a destination. That's known as a successor. So the best routes from the topology table, or the successor routes, are installed into the routing table. Those routes there are considered to be your successor routes. The routes that aren't considered to be successors, so they aren't the best routes. Those routes that are still pretty good, though, are considered to be feasible successors. They're not good enough to be in the routing table now, but potentially down the road they could be, depending on circumstances. And because of the fact that you can do different capabilities like variance and what they call unequal cost load balancing, I don't want to jump too far ahead, but basically the idea is if you have a successor route and you have a feasible successor, if the feasible successor isn't good enough to be installed into the routing table, what will end up happening is EIGRP loses a route. It'll automatically check its topology table and say, hey, do I have a backup route for this destination? If one exists, then that route is automatically installed in the routing table, and that information is flooded outbound. So it's flooded out to all the corresponding next top neighbors. Those neighbors receive it, and then they forward it on as far as it needs to go. And then now everybody has the updated information. If a feasible successor does not exist, what will end up happening is that route, the EIGRP table will take a look at that. No feasible successor is found. And then what ends up happening is the network goes active. So a bunch of queries go out and they try to find out what's going on in the network. So they'll ask all the direct connected neighbors, hey, I had this route, do you know another path to get there? And if nothing exists, then you get a response back in. It says negative, no I don't. If you wait a certain period of time, it's called the active timer. If you go so long and you don't get a reply back inside that active timer, it's considered to be what they refer to as a stuck and active. A stuck and active is going to, if a route goes in stuck and active, it is withdrawn from the routing table, and then that route is now considered to be down. And 99% of the time, that means that the link between you and the other router goes down too. So if you lose the network, now if it's just a network that you advertised via, it was directly connected, and that route will get removed. But if it was only a connection between two routers, and that connection goes down, then it'll end up happening is the neighborship will go down as well. So we'll talk about that more in detail later. But we have a granular metric, and there are multiple factors that go into to figuring out what's going on. People like to call it a hybrid metric. But basically, at the end of the day, you have a couple ways of looking at this. You have the default values, which are bandwidth and delay. So basically what EIGRP is going to do is take a look at a particular subnet you're trying to reach. This is considered to be the destination. And what ends up happening is you find the slowest bandwidth from source to destination, and if you find that particular bandwidth speed, that bandwidth becomes the bandwidth you use to do your calculation with. They call it the inverse bandwidth, meaning the lowest bandwidth along the best path, I should say. And when you have found that, you take that value, so you take the inverse bandwidth, which could be 1 gigabit, could be 1.5 meg, it could be 100K, it could be 100 meg. Doesn't really matter what the actual value is, as long as it can find it. And then what it does is it takes the cumulative delay. So it takes a delay on a per connection basis. And it takes that information and then it adds up all the delay from source to destination, takes the cumulative delay, so all the added up delays, takes the inverse bandwidth, it adds them together, and then that value is ran against a 10 to the 7th divided by 256, and what you end up doing there is you get your metric. Now there are other contributing factors that go into that come into play, but the general idea behind it is you have a hybrid metric to come up with a unique metric, and we'll talk about that more in detail when we get into it. But for the most part, you don't mess with the metrics. If you do mess with the metrics, they have to match on a per connection basis. So what ends up happening here is if you go in there and mess with the metrics, which by default is bandwidth and delay, but you could also throw in there load, reliability. MTU is a K value, but it's never ever been used as a metric in the actual calculation process. So then we have that piece. So once that's all figured out, then the metric is used to determine the best path. Unequal cost load balancing. Eigrp is the only IGP that supports it, and basically what you can do with that is you would take the best bandwidth, or I should say, you would take the bandwidth that you're currently using, and you would multiply it by 2. So you could say, because normally the lowest bandwidth, the variance is going to take the best route, and it's going to take a look at the metrics. And it's going to take, with a variance, you're going to say a variance of 2, which means you're going to take the best metric and you multiply that by 2. That could be the worst metric. So as long as your worst metric is a lower value than the absolute worst highest value, if you took the best metric and multiplied it by whatever the variance is, then that would be considered to be a that could be installed as a backup route. And that what would end up happening at that point is that backup route that was in the neighbor table, or I should say the topology table, can now get installed in the routing table. And then what you would do is you would have a traffic share, and you would send so many packets out one link and so many packets out the other one. Now I caution against this practice because of the fact that I have seen this in production break any type of hosted voice solution. Let's say, for instance, you're paying for a voice solution on the internet, and you're using SIP, which is a way for you to have a IP phone in your environment that you're not actually hosting. You have a connection out to the internet to another company, and they are hosting the call servers and all other stuff, and it's handled over the internet. Well, what ended up happening at that point is you have a connection between these two. Now, what will end up happening is with voice, if you have a single path from source to destination and from in the reverse path, what will end up happening is traffic will be a consistent flow. The minute you advertise an additional link in there where traffic can be load balanced, if you will, what you can potentially run into is what they call out of order packets. You can have starvation, to where depending on how you have your quality of service mechanism set up, you could have the wrong traffic classes put in the same traffic types put in the wrong traffic classes, and then you could have starvation of different types of traffic, and then you could get into really crappy call quality. And I've actually troubleshot this a couple times, and it's either going to be the internet that's going to be your problem, or it's going to be some sort of internal issue in your network where you have a routing, there's some sort of suboptimal routing somewhere in your environment. Now, I typically don't like to do unequal cost load balancing, and 99% of the time you don't see it. It's a capability that is not used widely. And then we have securing neighbor adjacencies. Now, you have only Md5 available in classic mode, and there's actually two modes to Eigrp. You have classic mode, which is what is referred to as autonomous system mode. So router Eigrp 1, and 1 would be the autonomous system number. And you have this newer one known as named mode, or multi-address family mode. And what this one does is you actually configure a named version of it. So router Eigrp CCNP, for instance. And then you would go and you type in address family, IPv4, autonomous system, whatever. And then you would go in there, and then you would configure your network and your Eigrp as such. With the classic mode, only Md5 is available for your authentication. With named mode, it supports MD5 and SHA-256. So the whole point of SHA is to be a much stronger authentication mechanism than MD5. MD5 is now crackable real time, according to Cisco. They've and a recent publication that I'm not sure if it was a publication or if it was. I heard them say it in a Cisco Live video online where they actually had issues where authentication was getting cracked real time, and they were having to change the password, and they were using MD5 authentication to do so with what they refer to as the rainbow tables, which basically means you're able to go out and take a hash that you see in the operating system, copy this into a website, and then as long as it's unsalted, which means there's certain attributes added to the calculation to make the hashing unique. If you were to add this to the rainbow tables unsalted, you would get somebody went out and created a bunch of MD5 hashes. They went out and they typed in a password, and then MD5 kicked out a hash, and so they were able to map that hash to a particular keyword or password. And so what you could do is you could go out there and you could take the hash, copy it into this website, and then you could see what the actual password might be. And sometimes sometimes it works, sometimes it doesn't. I haven't actually seen it used before, but the possibility is still there. And when we deal with MD5 authentication inside of both classic mode and named mode, you have to use a keychain to authenticate, and then we can get into automatic key rotation. Actually, I shouldn't say it's automatic. You have to actually configure the key rotation, but it'll automatically happen at a certain time based off of date and time. And we'll talk about that when we get into authentication. It's actually really, really simple to do. And then we have traffic engineering and optimization. So traffic engineering meaning you can go in there and you can use stub routing and summarization. Stub routing is going to basically tell a stub router is going to tell an upstream router, hey, if you have an active neighbor or you are receiving queries in, don't forward those queries down to me. And there's different ways of handling that. And then we have summarization. Summarization is taking a group of, say, /27 routes and aggregating them down to a single /24 or potentially even smaller subnet. So basically the idea is if you receive an active or a query in and you know a route is looking for an active, if the query comes in for a particular route and the longest match is the summary, that is going to be the edge of your query boundary. The query boundary is marked based off of summarization and stub routing. So if you can't advertise a query down to a stub router, and I can show you in the syntax where it'll actually tell you this. But that's basically telling you is the stub router or the spoke is a non-transit router, meaning it's not going to you're not going to use another router to you're not going to use that router to reach through another router to get to where you need to go, because that's going to be the end of the network. So basically, you're talking about the edge, the access layer, if you will. And then we have ACL filtering and route manipulation. You can go in there and you can create a prefix list to filter out a particular subnet in a distribute list. You can do route manipulation through redistribution and using tags. So there's several different features and capabilities out there for you to use. How you go about doing that is up to you, but that is pretty much the extent of how all this stuff works. We're going to get into all of these concepts as we go along, and we'll be running Eigrp in our environment over here. Let me pull up GNS3. We'll be running Eigrp here, and then over on this guy right here. So the idea, and this will happen down more or less when we get into DMVPN. I will show you guys how to run Eigrp over frame relay, which is really, really simple to do, and how that would come into play. But for the most part, we're going to be spending the majority of our time is going through the concepts and the understanding of how the protocol works. So once you have those down, and we get into DMVPN, after we get done with BGP and GRE tunneling and route redistribution, DMVPN will come in at that point, and then we'll run DMVPN, and we'll run Eigrp over DMVPN and OSPF as well. So once I have Eigrp done, I'm going to leave it intact, and once I have OSPF done, we're going to actually bring our EIGRP and OSPF domains to meet on routers 6 and 13, and we're going to do some redistribution there. I'm going to talk about how you can protect routes from being propagated and different features like that. So that's the wrap up for EIGRP. It's pretty straightforward as the overview, and then I'll start digging into the concepts and start showing you guys how stuff works as we go along. I hope this has been informative for you, and I'd like to thank you for viewing.